What's up, everyone? This is LeetCode 133 clone graph. We've done this in Python. Now we're going to do it in C++. So we're given a reference of a node in a connected undirected graph, and we have to return a deep copy or clone of the graph. Each node in the graph contains a value, which is an integer and a list of its neighbors. This right here, right? Don't get confused. This is just basically how the test cases are set up. It's basically how explaining how they represent the graph in the test cases. In essence, right, it's basically telling you that it's first indexed, not zero indexed. So for example, this would be the first index and it represents the node, the first node, which has a value of 1, right? And its neighbors would be 2 and 4. Second index here would be the node with the value 2, and its neighbors would be 1 and 3. Here would be the third node. The third index would be the third node with a value of 3, and the neighbors are 2 and 4, right? And here the fourth index represents a node with the value 4 and it has the neighbors 1 and 3. So yeah, it's basically, this is just telling you how they handle setting up the graph as far as the test cases go. Your actual input is just the first node, right? The starting node. The given node will always be the first node with value 1. You must return a copy of the given node as a reference to the clone graph. Okay? So yeah, don't get too confused or thrown off by this. So how are we going to handle this, right? Well, first of all, we cannot return the original node, right? Because you can't return the same graph, sorry, because you're not actually doing a copy, right? Node with value 1 was not copied, but a reference to the original one. So you can't just return, we're given the first node, right? We can't just return that node, obviously, because we're not doing a deep copy in that case, right? So we need to do a deep copy, and an additional case we need to handle is make sure that it's properly set up. Like here, for example, we have, for 1, we have neighbors 2 and 4, but here the neighbors are 3 and 4, so this would not work either. It has to be a complete deep copy, right? So keep that in mind, right? Now the way we're going to handle this is a hash map, right? Now, why do we use a hash map, right? The point of the hash map is we can store a node that we're on as a key, and after we make a deep copy, right, we store that as a value. And the point of this is setting up the neighbors properly, because let's say we make a deep copy of node 1, right? Okay, we set up the neighbors, right? 1 and 4, right? Now when we're at this 2, and we're checking the neighbors, we would create 3, right? Sure. But like, would we really want to create a node 1 again? No, right? Because we already have it. And how do we know that? Because it's in the hash map. We already created a deep copy of this one, so why would we want to create another one, right? We would not get the proper deep copy of the graph if we do this. So it's kind of the point of the hash map is it serves as a check to basically clone the graph properly. So you don't like reclone, or you don't do deep copies of nodes you already have, right? You only want to deep copy a node once, right? So the way we're going to do this is, first of all, let's check the constraints, right? All these constraints are important, but especially this one, which is that we can have 0 nodes in the graph. So that's an edge case we need to handle, right? So we're going to say, if there's no node, right, let's just return null, right? Okay. So let's make our hash map. Okay, so we're going to say unordered map node. Again, we have the original node and then the deep copy node as a value. And we're going to just call it clone. Okay. So first of all, we're given this input, right? But we need to handle this problem recursively, right? Because we need to touch on all the nodes and clone them properly. So let's make a function. We're going to call it DFS. You can do this using a BFS, but I think DFS is just easier. So we're going to do this, right? And sorry, I should actually put this. Put this in its own function. we're actually just gonna put this in here. Actually, move this up, move this back. Okay. Now, in this function here with our input, I mean, I guess you could include this here if you want. I mean, it is just like an edge case handling, so it's whatever. But down here is where we're gonna call it, right? So we're given an input, the first node, and we're gonna call DFS on that, right? So we're gonna say return DFS node, right? And in here is basically where we actually do everything. Okay. So in here, we're basically gonna check. So if the node that we're given in the DFS function exists in our hash map, let's return the deep copy, right? So basically if node, or we can, well, this isn't C, this isn't Python, C++, so we would have to do if clone dot count node, right? If the node exists, then we just return the value. Because again, the original node is the key, and so we need to return the deep copy, which would be the value of the hash map. We would say clone node. Okay. Now, down here is the case where the node doesn't exist in the hash map, so we need to actually do the deep copy, okay? So we would say node copy, we would say new node value, right? And we need to set it in the hash map, so it's a clone node is equal to copy, and we would say we'd have to actually return the copy, but before we return the copy, we need to handle the neighbors, which is actually important. So this is the part where I think it's easy to get lost. So let's handle this. So we're going to say for the neighbor of neighbors, right? And you just need to remember, like, when we're on a given node, we have a value, but we also have neighbors, right? So we can access both. So when we're at a given node, we create a deep copy of it, or it already exists. Awesome. So now let's handle the neighbors, because again, we're doing this recursively. So we need to go, when we're at this one, let's check this 2 and this 4, right? If they don't exist, the deep copies don't exist, let's create them. Otherwise, just return the value in the hash map, which would be the deep copies. So either they don't exist, the deep copies of the neighbors. When we're at, from the original graph, we go to the neighbors. If those nodes don't have a deep copy, right? And how do we know that? By the hash map. If they don't have a deep copy, we'll create them. Otherwise, we just return the deep copies. That's basically what we're doing. Okay. So we would say copy neighbors dot push back, right? Because we want to actually append the neighbors to that copy that we made, or that we already have. And again, like when we're at this 1, we set the neighbor to 2, so technically we're only pointing to 2. But when we're at this 2, we need to set the neighbor to 1, right? Because this is an undirected graph, right? So it is bidirectional. So that's why we need to do this. And either, regardless if even if we set the neighbor of 1 as 2, we need to set the neighbor of 2 as 1 also, because it's bidirectional, right? So just keep that in mind. And again, we want to run this recursively on the neighbor, right? If it doesn't exist, we'll create it. Otherwise, we just return it if it already exists in the hash map. The deep copy. Okay, got my my semicolon. I think that is it. Yeah. So yeah, not too bad. I hope I explained that okay, right? Just make sure you understand what we're doing here. I think this is probably the part where you might get the most confused, because I feel like all this other stuff is a little bit more simple. This right here, really, we're just appending neighbors to the copy node that we're on, right? And the way we append the neighbors is they either exist and we just append it because we return up here, or the neighbor doesn't exist and we actually create a copy and append it that way. Because again, you just need to remember, we're doing this is a DFS, we're doing this recursively, right? So that's how we're getting the neighbors. And that technically goes even deeper into itself because we keep going recursively, the neighbors of that neighbor and so on and so forth until we touch all the nodes. But I hope this helped. Okay. I think I submitted, but I'll submit again. But yeah, I hope this helped. I think this problem isn't too hard to understand. Maybe a little bit hard to come up with on your own though. But I hope this helped, and I'll see you in the next one.